One of the leading use cases for artificial intelligence for humanity is the emotion analysis. Why is emotion analysis so important? Because it can scan the face of, let's say, people who wear virtual reality headsets and detect their emotional well-being. Then it would give them recommendations about what type of activities would help them relax, what type of activities they're stressing them out. Emotional analysis is basically like having somebody observing you all the time, and through your face, sometimes when you feel in a specific way, your face cannot hide it. Not many people have that poker face. So the facial analysis is extremely helpful tool for medical purposes, for helping with mental health management, but it's also one of the most riskiest methods for analyzing data. The Information Commissioner Office, the ICO in the UK, they regulate data privacy. They consider emotional analysis to be extremely sensitive area, especially for people who have mental health problems. Now, if you wanted to help somebody with mental health problems, the easiest way is to analyze their expressions. But according to the Information Commissioner Office, that category of people belongs to a vulnerable category. So we have to take special precautions when we analyze data from vulnerable groups, which means we really need to think about how do we secure, how do we store, and how do we share that data. One of the key problems is that if you're using virtual reality headset, quite often the data is sent to the cloud, analyzed in the cloud, and then sent back. The device itself is not performing the analysis. The AI algorithm is based in the cloud. And having that long explanation about why we need to have these security mechanisms in place, that the Information Commissioner Office is imposing that regulation, and rightfully so, then these algorithms for privacy preserving analysis, they come into effect. And one of those algorithms, cryptographic algorithms for analyzing data without sharing the full data set with the general public or with the people who are analyzing data or with the cloud storage providers, it's the homomorphic encryption. Now, homomorphic encryption is one of the fairly challenging topics to explain. In this video, I'm going to be using a whiteboard because explaining it just with words and the video is not going to be easy. We need to have a formal lecture style, and I'm going to be using the Apple whiteboard for this. What is homomorphic encryption? The term homomorphic, it just means that it's using algebra. That's the fundamentals behind homomorphic encryption. And it's basically using two structures of the same type. That's the second explanation. How it usually works is that you would have two groups, so group 1 and group 2, or two rings, or two vector spaces. And in those groups, a form of encryption is required that would allow users to perform binary operations on the encrypted data without decrypting the data in the different groups. So they would be able to perform operations without decrypting the data. And that is the fundamental value of homomorphic encryption and how it helps in terms of preserving the data privacies of the participants that they are in the group. So what are the advantages of the homomorphic encryption? Well, there's various advantages, but firstly is that it would enable organization A, and let's say organization B, and this could be hospital 1 and this could be hospital 2, it would enable them to share the data and to analyze the data between different patients without sharing the data of the patients. So, for example, if a patient has been diagnosed for a specific condition in hospital A, but hospital B doesn't have that kind of diagnosis, the analysis could be performed in hospital A, and the final results could be shared with hospital B, but not the information about the specific testing and the conditions. So the user won't be, whoever is the participant in that study won't be disclosed. That's one in a simple explanation. Other use cases that this would be applicable, think about banks. So it doesn't have to be hospital. It could be bank A and bank B, and they have their own customers that they're storing money in there, and they want to create some kind of analysis about the financial stability of the overall economy or of the banking sector. Well, they are not allowed to share data about the individual customers, but they still need to perform this kind of analysis. And here it becomes interesting how that process is happening. Well, first is, well, there's three different processes in homomorphic encryption, and you don't have to use all three. You can choose the one that is the most applicable to the case that you're running. So with the first one, this one is the partially homomorphic encryption. With that one, you can only perform one operation, but you can perform the operation multiple times, and you can only perform addition or multiplications in this one, but you can perform them as many times as you want, and that's the partially homomorphic encryption. The second stage is the second type, the second method for homomorphic encryption is called somewhat homomorphic encryption. And here you can have both addition and multiplications, but for a limited number of times. So here is the difference between this. You cannot perform it constantly forever. And then the third one is the fully homomorphic, where both addition and multiplication can be performed infinite number of times. So that's the arbitrary type of computations that you can perform there. And what are some of the most famous algorithms within the homomorphic encryption? Well, first is Pallier crypto systems. And it belongs to the partially homomorphic encryption. We can only work with additions, but you cannot work with multiplications with this specific algorithm, but it's the most popular algorithm in the category. What other considerations we need to have when we're considering if you should use homomorphic encryption or not? Well, first, it's a very interesting field of cryptography, but you require cryptographers. So why would you use homomorphic encryption? Because if you need to perform privacy-preserving computation. If this scenario is not applicable to the data that you have, then homomorphic encryption is just going to make your life difficult. It's going to cost more money. It's going to require more specialists to perform this. But if you have to perform it, in which scenarios it would be valuable? It's valuable in scenarios where information is sensitive and it needs to be processed securely, especially if that is in a cloud environment or in distributed environment. So in the context of cybersecurity and artificial intelligence, homomorphic encryption has several implications. So let's stick to 3 or 4, because to expand too much, it would take over the entire section. So first is that it provides secure outsourcing of computation. So the homomorphic encryption allows the data owners to securely outsource the computation of their encrypted data to a third-party service provider, such as the cloud providers. So the data could be analyzed there. And this is essential for protecting the confidentiality of the data, but you can still get insights from it. So maybe Bank A does not have the processing power, or the knowledge, or the cloud services, or any of that IT-related tasks to analyze this data, but they can outsource that. They can send it to a cloud provider and they would be able to help them. The second is the privacy-preserving machine learning. So for applications of homomorphic encryption, this could be used to, hold on, let me switch off the phone, keeps bleeping. So for privacy-preserving machine learning, for AI applications, homomorphic encryption can train machine learning models on encrypted data. And this is helpful when data privacy is a concern. So for example, in healthcare, so if we have a hospital A and hospital B, that they're trying to train a specific AI algorithm that would detect those kind of illnesses in advance without human intervention, then they can use homomorphic encryption in combination with secure multi-party computation, which we will cover in a different video. And in this combination, the homomorphic encryption still plays an essential part of the secure multi-party computation. Third category is blockchain and smart contracts. So if you have interest in blockchain technology, so let me just put this. If you have interest in that technology, homomorphic encryption can improve the privacy and security of smart contracts. So it would allow the computations on the encrypted blockchain data and to preserve the data integrity and the confidentiality. So you won't really need to show the data because the blockchains are usually completely open. But now there's the emergence of privacy-based blockchains where transactions are slower, but confidentiality is preserved. Now, many of them are not legal. So the question is, how do you make the blockchain legal and still be able to preserve the privacy? Well, the homomorphic encryption is one of those solutions. So what are the fourth and final section of this video tutorial? What are the challenges and the limitations? Well, we have to mention that homomorphic encryption, it has computational overhead, and this can be substantial if you have a complex operation. And I work as a postdoctoral researcher, and I can tell you that we're constantly working on improving the efficiency of these homomorphic encryptions, but it's not easy. It's not as easy as you would imagine. The efficiency is a problem. And on that note, I think we are better leaving this topic at that stage, because now we know that there's a partially homomorphic encryption models, there's somewhat homomorphic encryption models, and there is fully homomorphic encryption models. We know that homomorphic encryption is based on algebra. We know in which scenarios it's used when you have banks, Bank A and Bank B, or Hospital A and Hospital B, that they have their own data which you cannot share with other banks and other hospitals, but they want to analyze data that is applicable to both of those banks, such as banking stability modeling, for example, and they can apply homomorphic encryption for that. The most famous model is pi-layer crypt system, and it's also applicable for secure multi-party computation and to blockchain technologies.